Hello, I sincerely welcome you to the course on how to obtain the Google Cloud Professional Cloud Architect certification. My name's Danny and I'll be leading the lecture with you from now on. I'd like to introduce the course for the first time. Our course is a theoretical explanation and problem-solving lecture for obtaining Google Cloud's Professional Cloud Architect certification. Now, we're going to focus on theory for about 40% of the lecture, and the remaining 60% will be problem-solving lectures. Especially in the case of theories, we do not explain the basics such as what a server is and what a DBMS is, but other CSPs, unlike Amazon, I will only touch on the key points such as the unique features of Google Cloud or the points that are frequently asked in questions. After that, since obtaining a qualification is our most important goal, problem solving is most important. Hence, I'll first lecture on related theory and then solve the problems. Since the problems are almost the same, if you memorize or understand the problems as they are, you will have no problem taking the test. We don't have an official cutoff for passing yet. But if we check various databases, it is known that if you get around 80% right, you can pass the test and get the results right away. So now let's look at the qualifications. The certification we are preparing for is Google Cloud's Professional Cloud Architect, and our exam time is scheduled to be a total of 2 hours. However, if you take the test once, you will see that most test takers usually finish the test in about 30 to 40 minutes, so you can understand that there is plenty of time. Next, we will explain that the certification is initially only available offline, but recently it has become available online as well. However, when taking the test online, I would like to tell you that you should prepare a room where you are alone or something like that, to check the surrounding environment and whether there is any risk of cheating, rather than taking the test anywhere. The current cost is estimated at $200. If you're a college student or just a student, there are programs that support vouchers for programs like StudyJam, or if you're working for an IT company, Google Cloud vouchers may be provided by the company. If you check that out, you can take the exam at a slightly cheaper price. Currently, the languages offered are English and Japanese. There are probably many people who are more comfortable with English than those who can only speak one language. So most of them will probably take the exam in English. This Google Cloud Professional Cloud Architect certification has some unique features. The most notable features is that case questions are asked. Case questions provide a description of the enterprise based on the real enterprise case. Now, the guide is given as a story, such as what kind of company this company is, how many transactions are made per month, and what kind of pain does this company have. After seeing that story, there are problems that come up where you can solve the company's pain points by utilizing Google Cloud. Fortunately, the cases from the companies that are being tested are now provided by Google Cloud, and we plan to organize those cases all at once at the end of the lecture. Then, in the case of exams, it is a regular schedule since there are tests scheduled at least 8 times a month and up to 20 times a month. And you can take the test whenever you want. And after taking the test, you can immediately find out whether you passed or failed. So now, the picture on the right is my certificate. In fact, now they are issuing certificates and giving out souvenirs as gifts. So since they give out things like fleeces and water bottles, I hope you take the test, pass, and receive a souvenir. This concludes the lecture introduction. Now, the goal for the certification is to get a passing score rather than a high score, so it requires a bit of selection and focus. So if you say that you know a little bit about servers and such, because you're in the infrastructure field, you can skip the theory part and focus more on the problem-solving lecture later. Then I'll start with proper bits that we need to go through. I'd like to introduce myself as the instructor. My name's Danny. I have a professional cloud architect certification from Google Cloud. I'm currently working as a Google Cloud expert architect at a major domestic IT company. And last year in particular, I was selected as a Google Cloud All-Star in recognition for my efforts to solve pain points for many companies and deliver value through the construction of various systems with using Google Cloud. I've carried out many domestic and international enterprise-level Google Cloud projects and have diverse construction experience from game companies to global logistics companies. In addition to Google Cloud certification, I also have certifications such as SQLD, Information Processing Engineer, and Network Administrator Level 1. The image you see on the left is Google's Gen AI, Gemini, which is commonly known, but there is a specialized AI for image generation called Imgen. I asked the AI to make a profile picture, and this is what it came up with. So I'm including it here. Let's work hard together to obtain Google Cloud certification. Thank you. Hello everyone. Welcome to the lecture on obtaining Google Cloud Professional Cloud Architect certification. In today's lecture, we will take a moment to look at the services of Google Cloud in general. Now, Google Cloud has various services. Those parts where the red star is drawn, those services are the most frequently asked as part of the problems. If I say that it's most frequently used as part of the problems, those are the services that's used a lot in actual companies or such systems. So when you have time, please search on YouTube, or searching the internet in general can help you get the certificate. Then let's take a look at them one by one. First, it's the compute journey, which we usually mean a server. Now, the most used compute engine is VM. There is a compute engine, and these days the trend is changing, moving away from VM and going more towards something called an MSA. In keeping with that trend, there is a Google Kubernetes engine called GK, which provides a containers and Kubernetes environment. So the compute engine is like that. In the compute part, the most frequently tested items are this compute engine and the Kubernetes engine. Next, serverless. Serverless is now called IS, and instead of creating infrastructure servers and such, Google takes care of managing and providing everything. And instead, users can enjoy the service, and we call it serverless. So that server, the serverless, now has cloud functions that run simple Python or JavaScript functions, and then there's a cloud run that runs the image container that's built. Next, there is a service called App Engine, which provides services that are normally run on the web or in the service environment. In a server environment on the cloud, these three things, they are usually the relevant ones, so I think you can use them as a reference. And Google now uses data analytics a lot, because Google now has open source original technology like Spark. There are various services based on original technology, so now the most frequently asked question is on BigQuery, which is a data warehouse solution that stores a lot of data for OLAP analysis, not OLTP, and can process queries quickly. Next, in order to build such a data warehouse, we need some kind of data pipeline. We pull data from the original source, process it to what I want, and then I collect that processed data into another database where I can easily view it. I have a pipeline for this every year. There is now an open source solution to automate that pipeline. There is a cloud computing company that has created a solution called Airflow as a service of the Google Cloud. Next, those of you who have experience with big data processing will have used something called Spark. So Dataproc is an open source that can process data quickly with a distributed system, and it has been made into a cloud. And now in data stations, we use something called a message queue a lot. There is a solution that uses Kafka, and it has an open source that has been made into a service of Google Cloud called PubSub. Okay, so these four are used a lot. I think you should know that next is a network. So to use the cloud, communication is now the most important thing. so you need to know some basic terminology. Now, the areas that are most frequently asked and tested are cloud passwords that are related to security, and then DDoS or web attack actors. Then there's what's called a content delivery network, or a CDN. So when we have a video on our server and a user accesses, say a user in Seoul or the user in US accesses a sub in Seoul, the video is so large that it causes a latency. However, if you use a CDN, you can provide static content very quickly because it is delivered from the network site closest to the user's location. That's why CDN provides this function. Now, there is Cloud DNS, which provides name server functionality. And then there is Cloud Interconnect, which is used when you want to connect an on-premise and a cloud. Next, load balancing is a service that acts as a load balancer elf switch to distribute the services of two servers for high cost formation. And then Cloud Router is a service that generally functions as a router. Then yes, so Cloud Routes and Router are now in a mutually secure relationship. And now, in the case of VPN, it's a service that is used when you want to communicate with other clouds or when you want to communicate with on-premise and VPN. Next, Partner Interconnect is a company that is now designated as a partner of Google Cloud. Through these companies, we are now interconnecting, and in this case, we can also receive high bandwidth services. So there are representative companies like this, Equinix, etc. So enterprise level is usually using Partner Interconnect to communicate. Next, there is a service called VPC, which is the most basic service in cloud networks. There are a lot of network services here, but the depth of the network is very low. Well, because there are not many additional features here, but rather it's a function that was used in the legacy and has been transferred to the cloud. So I'll tell you in advance that there is not much to it. Next is the database. First of all, now the big table, this is NoSQL. As is representative of a NoSQL service, then the spanner, if you create an insert, it creates data in the same place all over the world, and it can greatly reduce the race to access it. And it's a service that can provide a fast service in the case of Cloud SQL. You can think of it as the same as generally AWS's RDS, and MySQL. It's a service that can create DBs such as L, MS's SQL Server, and PostgreSQL. Then the data store is also a NoSQL. Memory store is also a NoSQL, and you can think of it as providing the same service as Redis. Now, continue using the cloud. If you look at it, you need to set up functions such as operation control alarms. So now there is a service called Cloud Logging, which allows you to check all the logs in the cloud. And then there is a service called Cloud Monitoring, which allows users to create their own dashboard monitoring dashboards. Then the CI/CD area is actually not on the one we are preparing for right now, the Cloud Architect certification. There is usually a separate section called Cloud DevOps, but since it's not covered much in that section, we will not cover CI/CD in this lecture. Yes, and the next big thing is the so-called integration service, which is an additional function that automates Google Cloud a bit more and makes it more convenient to use. For example, if you look at our server, there's a function called crontab in Linux. You can think of it as something that happens in the cloud. And then storage. File storage, essentially object storage, then block storage, then of NAS and NFS. This is what it is. This cloud storage is commonly called object storage. There are 4 types: archive, real-line, cold-line, and standard. Each has a different purpose and performance. These things are presented as questions. And then in the case of file store, it means NAS. You can think of the persistent disk as a normal block device that we can now mount and use in a VM. And if you go into the multi-cloud and hybrid area, This is now used not only for Google Cloud, but also for connecting with on-premise or other cloud service provider services, such as Amazon or Azure. This Anthos now links the Kubernetes cluster on Amazon based on the Kubernetes clusters on Google Cloud, or Kubernetes clusters on-premise. This means a solution that allows you to connect and use all of the Kubernetes clusters at once. Yes, and in the area of security, the most important thing now is IAM. Now, there is a menu that can manage users or users' rights all at once, and this is a migration. This is not a cloud that was used from the beginning. The system that was used in on-premise from the beginning is now usually transferred to the cloud and used. It's a service that's needed at the time. The service we see most often now is a storage transfer service, which is used to move storage on-premise to storage on Google. So this is a question that comes up a lot. Now, these days, it's the era of AI and machine learning. So as for related services, you only need to remember one thing. Vertex AI. Google Cloud has put all of its capabilities into one solution called Vertex AI. So we took a quick look at Google Cloud solutions. From next time, we'll look into each one in more detail and solve the problems together. I'll give you a short lecture about regions and zones on the next lecture. Thank you for staying with me for such a long time. Welcome to all of you who have come to obtain the Google Cloud Professional Cloud Architect certification. Today, we'll look at the region and zones. As you can see, the world map is currently displayed. You can see the points marked in black and blue. Now, this is referred to as the region, where Google Cloud is providing services. Now, if you look at the bottom left, it says current region, 3 zones. So this is a region, but this one region is composed of 3 zones. If you look over there, you can see Seoul as well. Then there are Seoul region, Tokyo region, Osaka region, and if we move closer to the US, there's the Oregon region, LA region, and if we go over to Africa, there's also the Australia region, which is quite a lot of regions. And this shows that these are composed of zones around the world. The Seoul region is usually composed of 3 zones. You can think of it as being composed of Zone A, Zone B, and Zone C. If we consider the Korean Peninsula in general, we have the Seoul region. While it's one Seoul region, I can't disclose the actual location of these specific data centers where the cloud is operating, but you can think of it as consisting of 3 physically separated zones, one at location A, one at location B, and one at location C. Therefore, one important takeaway is that a region is a broader concept, while a zone is a smaller concept. A single region can consist of multiple zones. There's a concept that is larger than a region, and that is called a multi-region. So what's a multi-region? It refers to bundling multiple regions together. So right now, we can take those in the West and combine them in one multi-region called the US, the EU West. Then we can also bundle Europe into another multi-region called the EU. So the important point here, if my service is targeted only at Koreans, is there really a need to make it a multi-region service? From an economic perspective or an efficiency standpoint, it would just be a waste of resources and most of all money. So if my service is aimed at Japanese people, then there's no need to create a multi-region service. I can just set it up in the Tokyo region or the Osaka region. Also, if my service can afford some downtime, is it really necessary to implement something like this? No, not really. If the service can handle downtime, then simply configuring a single instance would be a more economical and effective approach. These kinds of questions often appear on exams, so if there is downtime, it won't work. Even if there is a failure, the service must be continued to be maintained. Instead, depending on whether the failure occurs in a zone or in a region, the allowable range is specified. So when it is said that failures occurring in the region must be allowed, it must be taken as instance, multi-region. Now, if a failure occurs in the rock wall, the entire region must still provide good service. So excluding this region, services should be provided in other regions like Jakarta or Hong Kong. And this is what we refer to as multi-region. So if I say that my service only needs to cover failures that occur in good areas, then first I would create a server in zone A, and then create a spare server in zone B to service zone A. If zone A encounters a failure, it would take over with zone C. This is typically the type of problem you'll encounter. So please remember this well. Currently, Google Cloud has a total of 40 regions and 121 zones. This isn't fixed. Currently, new regions are continuously being created and generated. Next, I'll mention that zones are still being generated. You don't need to memorize this exact number. So when you actually use the cloud, you must check whether the service is available in the region. For example, in the case of the compute engine, you need to confirm that it's being serviced in all the regions. I want to use the VMware engine, but right now it's only available in the Sydney region. In this case, you need to check in advance and either come up with a backup plan or make sure to explore other options. So you can think of it as starting from the smallest concept, the zone, and expanding to the region and then to multi-region. Therefore, the zone usually gets the name of the region with A, B, and C attached to the end. Now, let's first look at the criteria for selecting multi-regions. In the case of multi-region, it refers to services provided across multiple regions. Well then, since the region is diverse, even if there is a failure in one region, the service will not be interrupted. So an example of this is the multi-region tier of the Google Cloud storage. Now the second is regional service. So does this mean that it only provides services within that region? This is a service provided across multiple zones within that single region. It's being serviced in the sole region and it includes all of A, B, and C zones. This means that the service should continue regardless of whether zone A, B, or C fails. So even if a failure occurs in one zone, the service availability should not be affected. As an example, there is a higher tier bit service called Cloud SQL of Cloud SQL, which can be considered as Cloud SQL being configured among these. Next, there is a service in the third zone. This is a service that is only provided in a specific zone, which is the smallest geographical unit. So if a failure occurs in the zone where the service is generated, a service disruption is inevitable. For example, I mounted a disk that is only applicable to zone A before moving the VMware to Sol. But a failure occurred in zone A. In that case, a situation will arise where you cannot use the disk that is mounted as a temporary drive. So shall we try solving the problem? Please pause for a moment and try to solve the problem. Have you written down the problem? Let's check the answer together. So first, I'll read the problem. Your company creates software which users can download from the company website. Your company has customers all over the world. So it's a company that produces software and you can download it from the internet site. But the point is at the back, your company has customers worldwide right now. But I want to minimize latency. What should I do is the current problem? Shall we take a look? Let's see the answer. Multi-region cloud storage, multiple multi-region cloud storage buckets, one bucket per region. It means to provide one multi-region cloud storage service for each multi-region. So if we create storage like this, one in the US, one in the EU, and one in Asia, users can connect immediately regardless of which country they're in, thus reducing latency. So the answer is D, and let's take a look at the other options. A. Multi-regional cloud storage bucket. That's incorrect. Why? If it saves in a multi-regional cloud storage, for example in the EU, then whether you're in France, the UK, Italy, or Europe, anywhere, this means European people can access quickly, but users living in countries like the US or Asia, such as Korea or Japan, inevitably experience latency. So option A is incorrect. Now let's look at option B. The regional cloud storage is also incorrect. This must go with multi-region, and a regional storage bucket should be created in each zone. Well, then in Seoul, we'd already have to create one bucket in Zone A, one in Zone B, and one in Zone C. This is not a very cost-effective method. Shall we try option C? Okay, the multi-region class storage has come out, but the back part is wrong. We will create one for each zone and region. Multi-region class storage is expensive, so we will create one for each zone. This is a very wasteful case of spending money, so C is also wrong. So the correct answer can converge on D. So everyone, this problem will actually be presented exactly the same in the exam, so please don't just solve the problem roughly. Make sure to remember the key keywords and the key keywords in the answer as well. Hello, and welcome to everyone who has come to obtain the Google Cloud Professional Cloud Architect certification. From this session onwards, we'll take a closer look at Google Cloud's infrastructure. In this first session, we'll learn about Google Cloud's compute engine, which we commonly refer to as VM. Now, when we talk about infrastructure, we often classify services in the cloud as IaaS, PaaS, and SaaS. Here, I stands for infrastructure, P for platform, and S for solution. So when we talk about SaaS, it means fully managed services where users don't need to worry about usage or performance. The cloud provider manages everything, and users simply use the features. And IaaS, on the other hand, requires users to cover much more, such as specifications or performance. Users manage these aspects, but there are risks involved. However, this allows for a bit more autonomy for the users. Google Cloud has IaaS, PaaS, and SaaS. So it's important to know which solutions correspond to IaaS, what proposal elements there are, and what functions they perform. So, in the future, we'll have a total of 4 corresponding to Google Cloud infrastructure. There are 4 of these, and today we'll take a look at compute engine specifically. Even if you're hearing about GKE or App Engine and Cloud Functions on Google Cloud for the first time, you don't need to worry at all, because the preparation for the subsequent lectures is in place. Now, let's find out what today's goal of compute engines is. First of all, this compute engine is commonly referred to as a VM. So VM and a server, that's why it's not just limited to specific languages. If you install packages on this VM and then install the language you want to use, you can use all the languages you want. There are no restrictions on the use of languages, like Python, Java, Ruby, and etc. So, while we secure a lot of autonomy without restrictions, Google Cloud only provides the infrastructure. We refer to this type of service as infrastructure as a service. Essentially, it's because we do not manage it. In the case of VMs, if we set up auto-scaling, when a certain CPU load is reached, we can increase the server specifications or the number of instances, enabling automatic auto-scaling. And VMs handle the most common workloads you can think of it. Essentially, it's the most universal infrastructure of Google Cloud. It can run any typical workload without the constraints of launching a web, a WAS, a DB, or a container. And yes, so now the table will be structured in my part towards the end of the infrastructure structure lecture, and I would explain it once more at the end. Now let's take a closer look at the compute engine. The compute engine is referred to as a predefined machine type or a custom machine type. When using a compute engine, we need to consider four main areas, and the first is the core and memory. In particular, when it comes to cores, it's not just about having a dual-core CPU with 8 GB of memory. There are a variety of families available. The most commonly used types include the N1 type and the N2 type, and then if I need something with a GPU or a specific high memory or high CPU, there are various types like A2 and N3, etc. So first, I decide what type of CPU to use and what machine type to choose. And then I determine the number of cores. After that, typically, memory is set based on the number of cores multiplied by 4 or 8. But I feel like this is too much memory. When I said my workload doesn't need memory, you can usually use memory accurately as well. In other words, when we refer to the standardized N1 standard 8, it has a standardized machine template with 8 cores and 32 GB of memory. But I don't want to use the 8 cores 32 GB setup. When I say I want to use 16 GB with 8 cores, you can persuade them to use a custom machine type to get the desired cores and memory. Next is storage. Now, storage has quite a few considerations that need to be taken into account. First, you need to choose whether to go to that storage in the zonal region or the regional region. If it's a VM, it will obviously be in the zonal region. There is one disk attached to the VM, but this disk is in the zonal region as well. So if this zonal disk is in zone A, it was said that an outage occurred, meaning a failure has happened. So, shall we copy the template and create a VM in zone B? But what about zone B? It cannot mount the disk located in zone A. So if I want to set up a cluster for the VM, or want to have high availability, what kind of disk should I create? It should be a regional disk, but in return, the cost will be higher, right? So there are these aspects. However, for those who say they don't need high availability or don't need to set up a cluster, they might choose a zonal server due to cost advantages. But if I absolutely need to ensure high availability and continuity, and I'll be clustering, then it must be a regional disk. You need to make this selection, and then there are two types of disks. There is commonly the HD and the SSD. Definitely, this one is faster. But the price of the hard disk is obviously a bit more attractive. The price is cheaper for the hard disk, while the SSD is a bit more expensive. So, you need to consider these factors when choosing the disk type. Now, for local disks and local SSDs, if we look at the cloud structure, there is a space where the server exists, and then there is a space where the storage exists. So, the storage is virtualized in a certain way. Specifically, it configures in such a way that it throws a specific capacity to the server side. Local SSD refers to disks that are directly attached to the server. So what advantages does this have? The speed is very fast since it uses disks that are directly attached to the equipment without going through any cables, and hence the speed is fast. However, the downside is that if the server is shut down, the data will be lost. So, local SSD is used for this purpose. Now, cloud storage refers to what we commonly call Google Cloud Storage, a bucket known as GCS, and it can be mounted on a VM for use. This is not a disk block device. it's an object device, I can say that there are a total of 3 possible configurations for storage. Next is networking. In terms of networking, we need to know that there is an IP, which can be an internal IP or an external IP. Now, next we have something called network tags. Network tags, if a specific tag is attached to a certain server, those servers will follow certain rules, such as routing, and at the same time we can apply both the firewall and routing. It's a very effective method. So, in networking, just remember IP and network tags. Now, what about below? The Linux or Windows part is an OS area. So, when I run it, and when I say that the workload is based on Windows, you obviously need to select Windows Server. And if not, when I said that my solution runs well on Linux, you can choose Linux. So now, Google Cloud also provides the latest OS every time the OS is updated. In the case of Linux, especially Red Hat Enterprise Linux, which is widely used in business, is naturally provided. Next, when we talk about SUSE, which is commonly referred to as ERP SUSE, Linux is required when the ERP is installed. Therefore, it is also provided by Google Cloud. Now, this is a paid Linux page, and this is when I don't have a license. You can include the license in the Google Cloud billing, but what if I say our company has a separate license? A BYOL, or bring your own license, you can apply the license you have to the VM in the cloud. Yes, then we will conclude the theory for our lecture here, and we'll probably go on to solve on some problems. I'll show you on the screen, so please pause for a moment and try to solve the problem. Then let me tell you the answer. The correct answer is C. So let's read the question together. The DB admin team requested something they asked to improve. They've asked to improve the performance of the new database server. So it seems they want to enhance the performance of the DB. Well, it seems that the DB is installed on a compute engine, which is not a fully managed service cloud SQL. So it's said that MySQL is running on Debian Linux. So increasing the memory of the virtual machines to 64 gigabytes, which is in option A, has to be incorrect. This is because the memory does not significantly affect the performance of the DB. So A is incorrect, and for B, well, we can't say that the performance is guaranteed in the second case. Each DBMS has its own strengths, and it cannot be option D. Now, option C, it's our answer, so we'll look at that last. Let's check option D. So move their performance metrics to BQuery. The reason why we're currently using MySQL is to handle OLTP transactions, and the term BQuery is commonly referred to as OLAP, which we typically use for data warehousing, so it cannot be the correct answer. Now, for E, for the purpose, we're modifying the batch job in the database, and we need to revise all batch jobs for each batch processor. This requires a significant amount of effort, so E also has to be incorrect. So C has to be correct. So why does performance improve as the disk size increases? This is important, so I'll write down in red. So as the disk size increases, The IOPS performance of the disk improves, and the performance known as the throughput will also improve. So the more you draw on it, the better the performance on the disk. Now let me give you an example. So is it better to have 3 40 gigabyte disks for different purposes, or one 120 gigabyte disk? The performance of all three will not be very high, so each directory will have a slightly reduced read or write speed. So therefore, when configuring on Google Cloud, it's better to attach one whole 120 gigabyte disk and either create partitions here or split it with LVM. This kind of work is necessary, so the answer can be chosen as option C. Now let's move on to the next question. Please pause for a moment and make sure you try solving the problem. So have you solved it? So the answer is C, and let's read it together. The preemptible Linux virtual machine, so let's talk about the preemptible. This is a preemptive VM that you reserve in advance. So let me give you this situation. So I've preempted it and used it, but now when I shut it down, then in my inventory, I cannot find the server. So this is because there are purposes for borrowing it briefly, just for a short time. It's not that I own the resources I have. Rather, I'm temporarily borrowing from the shared resources among the VMs. So, after shutting down, the VM that disappears need to be properly shut down. It shouldn't leave any of my information behind, right? So, what's important? When shutting down, it's crucial to completely erase the data there and then properly turn off the server solutions and to turn it off without causing any errors. So the answer is C. Now, let's talk about the shutdown script in the metadata. You say it's a country, but let me explain this a bit. There is something called metadata in the VM. There is something called metadata, and what it typically helps us with is managing label costs more easily, like in System A and System B. This allows us to check how much was spent in System A this month and how much in System B, which is what the label is for. Next, there is a script, and it includes the startup script. There is a script that runs when the server starts, and then there is a shutdown script. So the shutdown script is the one that runs when the server is shutting down, and including that will ensure a proper shutdown, right? Now, let's take a look at why the other option doesn't work. Option A. It means that you want to perform tasks on the OS, but it's better to do most tasks in the Google Cloud VM GUI console. This is because if you work on the OS, you'll need to take another snapshot and an additional task will be required, so A is incorrect. B is about registering a service in Linux, but since it involves work, it's also not appropriate. D also involves working at the OS level, so it's not suitable either. So the answer was C. So we're on the next problem now, so please pause for a moment. Have you managed to solve it? Now, the development team has installed a new Linux kernel, and the reason for the installation is to increase the speed of the batch process. It's been 2 days since the installation, and it seems that 50% of the batch server is gone on sale. So, they want to collect information. Now, they asked about how to collect information from the VM. Let's take a look at the answers. We'll analyze each option one by one. Option A mentions installing stack driver logging. This means installing a solution called stack driver on the VM and then configuring the settings file to specify which directories logs to collect, allowing the logs accumulated on the VM to be sent to Google. So, in the Google Cloud logging menu, you can manage the logs of all VMs at once. So the answer is option A. Next, debug GC activity log. So this is incorrect because we cannot know the logs generated on the OS. So option B is wrong. This is suitable for viewing logs that occur on Google Cloud. You can view logs by connecting to the serial console from the cloud or the cloud console. So this is incorrect. So this is correct. Sorry. It means accessing the VM. Now, what this is about is that the serial console is a method of connecting to the hardware not through network connections but directly to the VM on Google Cloud. That is a serial console, which is a feature that allows you to access the server regardless of network communication. So the answer is C. Now let's take a look at D. So what is this live migration? Live migration means any VM will run on some hardware, right? So the VM is running on the hardware, and if a hardware fault occurs, Google will automatically move the VM to another hardware. This is live migration. So can I check the logs for this? The reason this is wrong is that batch sub is said to be 50%. So that's incorrect. So this would be a problem with the OS, not the Google Cloud. So D is also incorrect. So let's look at E, stack driver, and then server metrics. When stack driver comes up, it means that all activities on the server OS are being logged. So that's the correct answer this time. Let's look at option F. Export the VM's image, then check the kernel messages. This is a slightly more roundabout way of doing it. So this time the answer for F was also wrong, so the correct answer will be ACE. I've solved a few sample problems like this, then I'll finish the explanation about the VM. Since we will solve many more problems in the lectures ahead, I hope you can get a sense of the types of problems that are being asked. Thank you for your hard work. Hello, and welcome to everyone who has come to obtain the Google Cloud Professional Cloud Architect certification. In this session, we will take a look at Google Cloud's Kubernetes engine, GKE. There is actually lots of theoretical content to cover, but we won't go through all of that in detail. Instead, we'll touch on the essential elements needed to solve problems, and for those who find this very unfamiliar, or are hearing these terms for the first time, there are well-organized documents available on Google or YouTube. And there are also short lectures that last about 20 to 30 minutes. So I recommend that you take a look at those first before coming. Now, let's go ahead and start the lecture. First, the GKE. Before looking at Google's Kubernetes, we will take a look at the structure and composition of the open source structures we generally use. The largest unit of the Kubernetes is the cluster. In a single cluster, there is one master node and several worker nodes. Now, this master node is what we call the control plane, and the worker nodes are generally referred to simply as nodes. Now, what is created on these nodes are pods, and those who have used containers will know that there are specific instances performing the same function and providing the same service. And those pods go on the worker nodes. The control plane, the master node, has various components such as a management server or a scheduler that manage these worker nodes. We refer to a collection of nodes in a physical or virtual environment that manages containerized applications as a cluster. And you can remember that a single cluster consists of a combination of a master node and worker nodes. Alright, then let's continue. Let's take a look at what elements are included in a master node control plane. Now, a control plane consists of 4 main elements, and you need to remember these 4 elements. First, we have an element called the API server. Second is a scheduler. Then the third is labeled CM, which stands for controller manager. Lastly, there is an element called etcd. So there are these four elements, and if we take a closer look at what each function does, the API server, which is not on Google Cloud but rather in a Kubernetes cluster, performs the most critical functions. When a user types a command, the actual tasks corresponding to that command are executed through the API server. Thus, the API server is the part that receives requests from all clients and components at the center of the cluster and performs the actual processing. Next, in the case of the scheduler, when there are pods that have not yet been assigned to nodes, it detects these pods and decides which node to run them on. So the scheduler observes the load status of these nodes and makes decisions like, I need to create a new pod on this node. That's what the scheduler does. Next, the controller manager plays the role of adjusting the state of the cluster or creating and deploying the controllers that control the state. And then etcd will serve as the data store. That saves all configuration data of the cluster. So, yes, in actual operations, etcd is very important. Because if a problem occurs in the cluster and etcd is well backed up, it won't cause significant issues for the service. This is because, based on the contents of etcd, the cluster can be quickly restored, allowing for rapid service recovery. However, if etcd is not backed up, it can lead to significant problems. Therefore, in practice, there is a trend to take backups of etcd in various ways. Now that we've looked at a typical Kubernetes environment, we should check how Google Cloud's Kubernetes engine is configured. So what you need to remember is that earlier, in a typical Kubernetes environment, there were the API server, etcd, scheduler, and controller manager. However, in Google Cloud's Kubernetes engine, the concept of a cluster is still the most significant. There's also something called the control plane, and then there's the node. Next, there are additional Google Cloud services that connect to effectively use this Kubernetes engine. Now, if we first look at the control plane, the API server we saw earlier still exists. However, we cannot say that it is exactly the same as the API server in the open source Kubernetes, because it is a service provided by Google Cloud with additional features integrated into the API server. Next, we saw the CM controller manager earlier, right? The resource controllers are responsible for creating or deploying the controls that manage the cluster, and then there is also a scheduler that handles scheduling in a similar way. Next, the storage is something that plays the same role as etcd. So the storage serves the same function. You can think of it as in this way, and moving on, a node refers to a worker node. When it actually creates Kubernetes, a VM is generated and pods are deployed on top of it. So multiple pods are deployed across various workloads for each service, and they actually provide the service. So to effectively use the Kubernetes engine, what Google services should it be used with? First of all, since it obviously needs to provide a service, a network is required. Next, when backing up data related to Kubernetes, a persistent disk will be involved. Therefore, the disk can be used in a mount, and since a service must be provided, a load balancer is needed at the top to manage various traffic, balance the load, and route the traffic to different cards based on the path. In addition, it would be good to know that there are various services needed when using the Kubernetes engine, such as container registries, managing images that are distributed, and elements responsible for the CICs. Now, this GKE also has a zonal service and a regional service. In the case of the zonal cluster, there is one cluster per zone, consisting of one control plane and multiple nodes. On the other hand, in the case of the regional cluster, there is one cluster spanning multiple zones. However, in this case, each zone will have its own control plane, which is the difference to remember. However, in the case of GKE, multi-regional clusters are not yet being serviced. Now, let's try to solve a problem related to Kubernetes. Please pause for a moment and try to solve the problem. Let's take a look at the answer. The correct answer is A. If we look at the problem, we're already using a deployment on the Kubernetes engine. Next, there is a service called the Echo deployment that's already exposed to the outside and is in service. However, at this point, we need to update the container with minimal downtime. The question is, which method should we choose? The answer is option A. Let's take a look at option A first. They say that by using something called an image, you can set the image deployment in the kube sheet like this. And the reason it's correct is that when you use the set command like this, it automatically updates the image through a rolling update, allowing for minimal downtime. This is the most standard method in the case of passwords. The rolling update of the instant group acts at the node level and does not affect application deployment. So option B is the wrong answer. As for option C, it indicates that the deployment will be deleted. kubectl delete. If you delete the deployment and create a new one, there will be a significant amount of downtime. Therefore, in a situation where minimal downtime is required, this cannot be the correct answer and is not suitable. If you update the YAML file in option D, it will affect how the service is exposed, and this is unrelated to the container image and image updates. So this method cannot be used to update container application companies, which makes it incorrect. Now, the second problem. Have you solved it? The important thing here is that we have an element called GKE. There are nodes and pods inside, and this is a service from Google Cloud. We need to manage it using the gcloud command. As for nodes and pods, there are elements within Kubernetes, so we need to handle or manage them with kubectl. So the answer is going to be B. And the statement is that this cluster is created with gcloud, and the deployment of the Kubernetes engine is done with kubectl, which was a relatively easy question. So let's confirm the answer is B, and move on to the last question. Please pause for a moment and try to solve the problem. The answer is B. As you can see, this is a microservices application. The development methodology that we commonly refer to as MSA is very trendy these days. In the past, we developed services in a monolithic way, where multiple services were hosted on a single server. Nowadays, we separate services independently so that we can quickly reflect the rapidly changing trends. Even if one service changes, I only need to provide the desired value without needing to know how the related service has changed. By doing it this way, we can bring a lot of flexibility to development. So MSA is a very trendy development method, and the infrastructure suitable for developing the MSA is by the Google Kubernetes engine. So what's the issue? We developed using the MSA method, and now we want to verify whether the application works well. When there are conflicts between services, so I said to choose the most appropriate method that can be verified. If we take a look at option A, now it says to add a paint to one of the cluster nodes. and then configure an opposing label on the pod. This is related to controlling the scheduling of the placement on the hard disk. This method is not suitable for simulating crashes in microservices. It's just a method where pods are simply relocated and scheduled. So it does not affect the actual service. Now, if we take a look at B, Istio is a component that manages the traffic of services within the Kubernetes. It simulates how Kubernetes clusters respond by injecting faults into the Istio, and B is the answer. So among the features of Istio, there is a fault injection feature that simulates various faults like delays or errors. Using this, we can observe how our developed microservices handle specific faults, making it a very useful tool. So the answer is option B. And option C involves deleting a node to observe its operation. This is not about microservices. It affects all services running on the node, causing service collisions and even larger faults. So it's not C. When we think about bypassing traffic, we can't actually confirm the simulation of collisions. So D is a useful feature, but when we want to see how it reacts to the collisions required by the problem, it doesn't seem to be the right choice for the customer. We've looked at Kubernetes like this, and now we're going to solve a lot of problems. I'll be bringing a lot of problems in the lectures ahead, so if anyone finds today's content too difficult, or if there are too many terms they've never heard of before, I hope you definitely look up Kubernetes on Google or YouTube. Thank you for your hard work. Hello, and welcome to all of you who have come to obtain the Google Cloud Professional Cloud Architect certification. In this session, we'll take a look at the serverless services. It's offered among our infrastructure solutions. When we refer to serverless, we also refer to it as fully managed services. Users don't need to worry about core, memory, or availability. Those aspects are automatically adjusted and handled by Google Cloud based on usage. This type of service is what we call serverless, fully managed services, and today we'll cover the three main services. So we'll look at Cloud Run, App Engine, and Cloud Functions. First, let's start with Cloud Run. Cloud Run allows you to deploy HTTP containers in a serverless manner, without worrying about cluster configuration or auto-scaling, and that's important. It's a service that deploys containers. So it functions similarly to the Kubernetes engine we learned about last time. The Kubernetes engine builds an infrastructure system that orchestrates containers on Kubernetes. You can think of Cloud Run as an environment where containers automatically run as long as you have the container image, specifically the Cloud Run image. Well, there are 5 advantages to using the Cloud Run. Let's take a look at them. First of all, this Cloud Run is said to be build neutral, which means it has a standard in the form of an Open Container Interface OCI form. It means that it supports container standards and various forms of containers. So what's good about this is that it is on premises. Then I can use the containers that I was using on another cloud in Google Cloud. Conversely, I can also use the containers I was using in Google Cloud on premises or in another cloud. This functionality becomes possible being build neutral. Secondly, that there is fast auto-scaling. Once deployed on Cloud Run, it automatically scales up according to the number of requests without the effort of managing a Kubernetes cluster. And if there are no requests, Cloud Run automatically scales down. Then it would have very cost-effective advantages. Next, the third point is that we can split traffic. So because we can separate traffic between different versions, we can usually implement sequential deployments like the Canary strategy, Canary deployments, or blue-green deployments. Fourthly, it's an environment wherein we create images and run them, so we can use user domains in ways that we want. Therefore, regarding TLS and other certificates, there will be no issues at all. And the fifth point is that automatic recovery is possible. So, in case there's a problem in any zone, this cloud will automatically handle redundancy recoveries. So, we've looked into Cloud Run, and how do we use it with the cloud? First, you code in your preferred language, and then you need to push the code to cloud. Build to create a container build. What this means is that when we create a container, we define the image as a source in the IP window. Now, we need to build this image from somewhere. So we can set up a container build system on a VM, or if I want to go with cloud-native solutions, if I want to build a system using only the features provided by the cloud, then the alternative is cloud build. So if I insert the image I created here, this build will create the image, and we will run the already created image on Cloud Run. You can understand it this way. Now, there is a command with the gcloud command. You can think of it as being able to have an environment where the container image automatically scales up and down. And this is according to request volumes with the gcloud run deploy command. So, when there is a request for Cloud Run, it automatically scales up and down, right? Now, let's take a look at what requests are involved in making Cloud Run work, such as HTTPS, gRPC, WebSocket, and PubSub connections. So the first three are probably familiar to those who have done a bit of IT. PubSub is one of the services offered by Google Cloud, and it's generally what we refer to as Kafka and message queue. So when a message is written in Kafka and received by Cloud Run, it will automatically operate as expected. So we've looked into Cloud Run, and now let's explore App Engine. So you can think of the App Engine as a fully managed platform, so things like Tomcat or JBoss have been deployed on Google Cloud. Then you can think of this as App Engine. So if we take a look at App Engine, it's a service that allows you to easily host and run applications on a fully managed server. So without needing to create servers or install anything, you just throw in your web source, and it automatically handles web traffic and allows you to use all APIs, which is what App Engine does. So App Engine has two tiers. There is the standard tier and the flex tier. The standard tier allows you to scale the instances of App Engine from 0 to n. So this is used when there is a sudden and extreme spike or drop in traffic. As for Flex, it also has a minimum of one instance. It can be expanded from 1 to n units. And Flex is good to use when the traffic is somewhat consistent and then regular. Now, let's take a look at Cloud Functions. The most important point about Cloud Functions is that they are event-driven serverless functions. What this means is that I can write a function in Python, Java, Node.js, or Ruby, etc. And when a certain event occurs, I want to execute this function. So, Cloud Functions are often used to build features that notify us when an alert occurs, or when there is a problem with a server. This is because they provide event-driven functions, but to use this Cloud Function, the supported languages are limited to a few, not every language in the world. It only supports languages like Go, Python, Java, Node.js, PHP, and then Ruby and .NET. If you programmed in a language that is not on the list, you won't be able to use Cloud Functions. Instead, you'll need to create an image with Cloud Run and deploy the service to execute the features you want. So, as I mentioned, Cloud Functions are event-driven. So what kind of events can trigger the execution of Cloud Functions? First of all, they can respond to HTTP requests, and then when a file is uploaded to cloud storage, it can trigger an event for the customer, indicating that a file has been uploaded. This allows you to automatically execute additional functions linked to the Cloud Function. as well as the pub sub mentioned earlier. Next, Firebase is a database used in mobile applications. After Firebase, or when some tasks are absorbed by the CLI, I can trigger and execute Cloud Functions in such cases. So when do we use this Cloud Function? Typically, we use it a lot during ETL processes, when data is exported from the database to a CSV file and dropped into cloud storage. We need to pre-process the data before loading it into an AP or a data warehouse. The trigger for that can be a Cloud Function. Alternatively, we can use Cloud Functions with webhooks, or we can also use Cloud Functions for mobile backends. Additionally, when creating applications with IoT capabilities, we can also utilize Cloud Functions. Now, you might think that Cloud Run and Cloud Functions serve somewhat similar functions. There are 4 cases where you should use Run instead of Cloud Functions. First of all, when I have a program in a language that I don't support in the function, then the function can be requested for a maximum of 15 minutes. But what if a longer wait time is needed for that request? Or when the amount of data is to be processed is large, and the scale of concurrent traffic is high, then it would be better to use Cloud Run instead of Cloud Functions. So we quickly looked at these 3 services, and now we'll try to solve a related problem. Please pause for a moment and try to solve it now. So we're encountering something that we haven't learned yet. Now, BigQuery and Bigtable are coming out. BigQuery is a data warehouse that stores a lot of data for analysis, such as monthly usage or total monthly sales, which is used for aggregated data. Bigtable, on the other hand, is a high-performance database that processes queries in real time or handles large-scale queries. So you can think of it as a high-performance database. Then, please try solving the problem. Have you solved the problem? The answer is B. Now, if you look here, there are currently 500,000 transactions occurring per second. So if that's the case, BigQuery is not the answer. So a data warehouse is good for any aggregation or large-scale processing, but for real-time incoming data, we need to go with Bigtable rather than BigQuery. So what do we choose here? Should we choose Cloud Run? Should we choose Compute Engine? You can check the criteria for this here. As for this service, well, when it's busy, it has to handle 500,000 requests per second, but there are times when such requests don't come in at all. So in the case of Compute Engine, it's suitable for applications that run 24 hours, but its specifications can be quite cumbersome to adjust. Because the server also needs to be taken down, after that, there is a procedure to start the application once the server is up, which makes it quite cumbersome. However, in the case of Cloud Run, we can easily scale up and down flexibly according to traffic, and there is no need for shutdown and restart stages when doing auto-scaling. Therefore, if traffic fluctuates, Cloud Run is more of a suitable solution than Compute Engine. So the answer is B. And from a pricing perspective as well, Compute Engine is relatively more expensive than Cloud Run. So when looking at the price, it was indeed the best choice in Cloud Run. Most of the exam questions come out like this, where a situation is given, and there are many options to handle that situation. So among those, the question might come out like this: I prioritize cost effectiveness, but I think performance is more important. So this is a typical type of question we need to prepare for. Thank you for your hard work today. Hello, and welcome to all of you who've come to obtain the Google Cloud Professional Cloud Architect certification. From this session, we'll take a look at networks, starting with the most fundamental concept, which is the VPC, or Virtual Private Cloud. The VPC is essentially a solution that plays the most basic role in networking within the cloud. In on-premises environments, it corresponds to the role of an L3 backbone. Therefore, the most basic unit for separating networks is the VPC. So if you look here now, the project shows networks 1, 2, 3, 4, and 5. And you can think of network 1 as one VPC, and this is the second VPC, and the third one is the third VPC. And it's structured like this. Now, if you look on your right, there are regions listed that can be used in Google Cloud. You can see that multiple subnets are assigned to one VPC, right? So VPCs, as we mentioned before, can be categorized into multi-region or region zones, but this is a global service regardless of that. One VPC can provide services for all previous instances without exception. So shall we take a look at the VPC? I created a VM in US East 1 after making the VPC, and then I created one in Europe West 1. Although A and B have different regions, they are connected through a single VPC and a single backbone. This means that A and B can communicate with each other without needing to take any additional measures. This is because there is a single network. So if we take a look at network 3, I've created a VMC in the US East 1 right now, but this one is currently connected to the internet. We have two ways to connect to the internet. The first is to create a NAT, stands for Network Address Translation, or we can assign an external IP to the VM itself. But we still don't know how VMC is connected to the internet, which of the two methods it is using. However, external communication is possible. If you look at the network 4, VPC4, there are some called VMD, and they are of course connected to the internet through NAT or external IP. C and D are currently on different networks. Therefore, even if they are in the same region, communication between these two cannot be direct. However, since there is a single connection called the internet, communication between these two is possible through this external IP or the internet. Now, there is a point where a problem will arise here. So can VMA without external IP communicate with a VMC? The answer is that it is possible. So they can communicate. How this communication is possible will be covered in the next lecture. But we have a feature called VPC peering. Peering serves to connect one VPC with another when there are multiple VPCs. So if we call this a peering, and if we do peering, and then A and C can naturally communicate with each other. So if VPC wants to communicate with an on-premises system, what should I do? There are also two good examples. I mentioned that VPC is not a global service at all. So we created subnets for US West and US East and made VMs in each. Well, in order to connect to the on-premises, we need to use a service called VPN, or there is also a service called Interconnect. So VPN logically separates the connection through external internet, creating a private connection. And interconnect means connecting directly with physical lines, which is a way to connect to the cloud. So I've set up this VPN on USS1. Therefore, when we communicate, this VPN will obviously allow for communication. Well, that's because we mentioned earlier that we can communicate within a single VPC regardless of the region. So, because of that, connecting to on-premises means that the respective region needs to create a VPN beforehand, and then it will be possible to communicate with the instances inside the VPC occasionally. Next is the subnet. The VPC is global, and it can be connected in various ways. Within a VPC, you can have multiple subnets. Subnets 1, 2, 3, and 4 are regional without exception. You cannot have a global subnet. The subnet is regional, so one region can have multiple subdivisions, but each subnet must be allocated to only one region. So, A and B may have different VMs that are similar but in different areas. So, can they communicate? Yes, because they are in the same VPC, all of the VMs can apply a unified firewall rule. This is because the firewall that we are talking about corresponds to the VPC. So if we define what the source IP is, what the destination IP is, what the port is, and whether to allow or deny these in the VPC, it can be applied to all VMs using that network, or only to those without specific network tags, allowing for bulk application. So subnet design is usually something cloud architects need to do, but there are some important considerations here. Of course, there is an offline version, and similarly, the subnet cannot overlap. Next, the subnet must have a unique CIDR block. So, if you had something like 10.128 with a 16-bit, then you need to segment it starting from 129 with another 16-bit. Now, when creating a new subset, it must be within the specified IP range. So what now? Suddenly having a score of 1065, which is a number that is impossible in a 32-bit world. Therefore, it must be within this unique valid range of IP. Next, there is a C-class range that we commonly refer to with the internal IP. You must also adhere to that range in the case of services like subnet. This is the point, expansion is possible, however, it cannot be reduced. I can currently use a 24-bit subnet and increase it to either 20 or 16-bit, but it's impossible to say I want to reduce it to 28-bit. Since you cannot reduce it further, you should avoid creating large subnets whenever possible. You need to take the minimum necessary. Whenever there are additional needs, you should use it in a way that allows for expansion. So now, there are various regions at the bottom of the network where you can create different subnets. And once you create that subnet, you can now create resources there. You can think of it this way. So, as we mentioned earlier, there were two types of IPs. There was an external IP and an internal IP. In the case of the internal IP, it is assigned to the VM from the subnet range through DHCP. So, what is DHCP? It means that some sensors have been created. What kind of IP should I assign here? I can specify the IP myself. I can designate the IP I want to use within the subnet, but there is also an automatic feature. When a VM is created automatically, it will dynamically receive an IP allocation through DHCP and assign it to the VM. So if I say that I want to prevent the risk of the IP changing when the VM is turned off and on again, you can reserve an IP. If you reserve an IP and then assign that reserved IP to the VM, this VM will always receive the same IP regardless of how many times it is restarted or how the DHCP is renewed. Also, when I create a VM, this VM and its IP will be automatically registered in the DNS within the VPC. Therefore, every VM must have a private IP by default, and depending on its usage, it can also have an external IP. The external IP is provided from a pool of external IPs that Google Cloud has, and one will temporarily be assigned and allocated from there. External IP can also be reserved. So I don't like it when my external IP changes. In that case, you can reserve that external IP and use it. But please note that there will be a cost for reserving an external IP. Charges are based on an hourly rate. So conversations are also possible. Next, there are cases where I need to connect to on-premises and must use a specific external IP. In that case, a BYO IP is available, the external IP of the VM. Can actually be assigned. However, here's another point. I had both a private IP and a public IP for the VM, but the VM only knows about the private IP. The public IP is actually provided as a NAT function, so the VM cannot know what external IP it has. So remember that the external IP is not shown and is mapped back to the internal IP. This is a brief overview of VPC. In our network session, there aren't really any issues related to the network. This is because there are separate certifications related to the network. So we will review the network at the end and solve problems then. And I plan to explain theory in this manner. Next, let's look into the shared VPC and then the private service connect, which is referred to as PSC. Thank you for attending the lecture. In this session, we'll explore the stages of Google Cloud resources. And then we'll discuss the concepts of shared VPC and private service connect that may arise from that. First of all, the smallest unit that can hold the resources of Google Cloud is a project. So within this one project, we can have resources like the VMs we learned about earlier, or Google Kubernetes engine or app engine. Additionally, there is a concept of a folder that can own the project above this project. Since it's a higher level concept, this folder can contain multiple projects, and if there is another folder, there will naturally be other folders as well. Now, folders can have this folder and other folders, so they can be a high level folder. Therefore, only the folder hierarchy can have multi-layers. And at the top of the folder hierarchy, and at the highest level in Google Cloud, there is an organization that serves as a collection of resources. This cannot have multiple instances. It must have one organization, and under one organization, there can be multiple folders and multiple projects. The organization is quite important. It must have at least one domain. To create 100, for example, if we say Coca-Cola, it would be coca-cola.com. If it was Samsung, it would be samsung.com. And that's a domain representing such a company. There could be samsung.com and samsungelectric.com, but Samsung Electronics doesn't have multiple domains like samsungelectric1.com, 2.com, etc., which is not how it's used. Therefore, you must use one domain for a company. This is how you can create it. So there's an example on the left. When we say organization company, if we have a company called ABC, we use abc.com, and then we create folders for each organization underneath. So some organizations divide folders a bit more specifically by team or task. Below that, there is a structure where projects are assigned to create resources. So the reason we talked about this today is that we are going to look into something called shared VPC. When can we use shared VPC? We can only create a shared VPC when my project belongs to a specific organization, which is why I explained the org earlier. If I said I'm just using a project as a standard-alone single project, then I cannot configure a shared VPC. So if you want to use it, you must definitely configure the org. Now, the shared VPC is somewhat important. This is because it's a concept that doesn't exist in Azure or Amazon, but only in Google. So this might come up as a question or an option in an exam. We learnt about VPCs in the previous session. VPC was a solution related to internet networks. Now, let's take a look. I'll draw a little picture. There was project 1, project 2, project 3, and then project 4. So here we have each one. Earlier, we had one VM each. And what did we need to create a VM? We needed a VPC, right? It was necessary like this. Now, we have 4 VPCs. If they all serve the same role, then we need to open the firewall on the same port. So, how many times do we need to open the firewall? It was specified in the VPC of the firewall. So, we need to open the firewall a total of 4 times in the VPC. Now, if I want this VM to communicate with the VM in project 1, then we need to set up peering like this. Next, I want to enable communication between project 1 and project 2. So we need to pair again. Now, since it's connected like this, number 4 or number 2 could also be communicating. But I mentioned that earlier you can't pair twice, you can only pair once. So this one is now the second time. So number 4 and number 2 can communicate through number 1. It seems like it's possible, but in reality we need to establish a new pairing, despite the lack of communication. If we use it this way, the repetitive tasks will increase significantly, and we also need to continuously consider the variable of pairing. So, how can we use it? If we use a shared VPC, we must have an organization, and there will be several projects within that organization, right? So, project 1. Next, let's assume we have projects 2, 3, and 4 like this. In the org, when creating a VPC for project 1, we make it into a shared VPC, then we have the VPC. The VPC here can be used in projects 2, 3, and 4. So, I created a VM this time, and I also created VMs for projects 3 and 4. Then, instead of using the VPCs in each project, we can receive IPs from the subnets configured in the shared VPC. So what's good about this? I want to open the common firewall for VMs 2, 3, and 4. So in that case, it only needs to perform the task once, which significantly reduces the number of tasks. Next, communication between 2, 3, and 4 is naturally possible because of the single VPC. If they're all in the same subnet, it's obviously possible, and even if they're in different subnets, routing will ensure that communication is still possible. So what else is good? In a company, there's usually one department responsible for the network. Now, if that department is split across VPCs, each team would have to divide their tasks, and then things like history and such shouldn't be followed. If everyone transitions to a single VPC, then records and tasks will be centralized, making management much easier. So that's the advantage of a shared VPC. On the left, there is an example of how to use the shared VPC. Let's take a look. But if we didn't have this shared VPC and used separate VPCs instead, then here we have VPCs 2, 3, and 4, all needing to communicate with on-premises. In that case, they would all need to connect through on-premises or some interconnect, right? Each of them would need to be connected, and the connection costs would be quite high, wouldn't they? Well, if you're using a shared VPC, you just need to connect to the VPN on top of the existing on-premises setup. And then all resources will be able to communicate with the on-premises environment, because it's one VPC backbone, right? So you can attach one VPN per region, create subnets, and then allow other users to create their own subnets. To assign to each VM is needed. So, for those who have used Amazon, this is very similar to what we call a transit gateway. With a transit gateway, you need to connect to each project, which is referred to as an account. However, in the case of Google's shared VPC, once you create it, it becomes very convenient regarding network management. I think you can consider it as easy to manage. Now, lastly, let's talk about the Private Service Connect. This is the Private Service Connect, which is a specific service within the VPC. What it does is connect to services like Google, DB, or file storage NAS. In cases like these, we don't want to expose them to the outside because they contain important customer data and very critical data for our company. Allowing external access could pose a significant risk of information leakage. So at the time, we use Private Service Connect. For example, if we use Cloud Spanner, BigQuery, or Cloud SQL, it would look like this internally. Those that need such protection are created in a dedicated network through Google's private API, rather than a general network. So here we have a VPC, Google's own VPC, and then we connect it with the VPC I have through peering. So the VMs in my VPC can access services like Google Spanner. This is through a service called Private Service Connect. This way, it becomes possible to conduct security audits on the network. Next, the specific age only applies to those VPC instances. This allows access to specific databases or file storage services. Then, the level of security will significantly increase. If we have Google's own VPC, it allows for the management of this. For example, if the storage server is unusual, we can create a backup list from it. And since we can receive such managed services, we should understand that services like databases or NAS must be connected to Google Cloud through Private Service Connect. So when we create a Cloud SQL, we need a subnet of at least 20 bits. Then, every time that happens, we add the IPA range to the Private Service Connect and create it, and then it can be expanded. Now, the shared VPC that we learned today, things like Private Service Connect, they don't come up directly in exam questions, but will appear in the options repeatedly. Thank you for your hard work. Hello everyone, and welcome to the Google Cloud Professional Cloud Architect Certification course. In this session, we'll take a look at load balancing. Load balancing can be divided into two types: global load balancer and a regional load balancer. If the service I provide receives traffic globally, I need to use a global load balancer. However, if I only receive traffic from a specific country, then I can use a regional load balancer. So, for each global region, there are three types of load balancing. So there are a total of 6 load balancers in Google Cloud. So if we take a look at how this load balancing works and what components exist, first, when traffic first comes in through the load balancer, we distribute the traffic into various infrastructure, several serverless solutions or storages. So in the load balancer, there is a front-end component, and we go through a process called health check. And behind this, there is the backend. And we'll take a look at them one by one. First, we have the front end. For the front end, certain settings need to be configured, starting with the IP of the load balancer. Next, the port for receiving the service needs to be set. Additionally, if it's for HTTPS, we need to register the SSL certificate. So, If we register the SSL certificate and then configure things like redirection for the front end. Now, regarding health checks, let me mention that in the backend, either VMs of multiple services or Kubernetes pods or various serverless solutions. Of course, it can be configured as a single instance, but usually it consists of 2 or more identical instances. And here we check whether we can send the service or all of these services up. Because if I send traffic to infrastructure that is not serving when the traffic comes in, that's a problem. So that's why checking which side of the backend to send the service is called a health check. This check involves confirming whether the port is listening and checking things, like the intervals. And once the health check is complete, it finally transitions to the backend, which is quite simple. The applications or services that I'm actually providing in reality are registered in the backend. And the type of backend is somewhat important. It's important to know what types of backend services are available, and the first one is generally a VM. So we have a VM, and we will see 2 types of it in the next slide. A managed instance group, and then there are 2 types of backends. A managed instance group and an unmanaged instance group. Secondly, we can also register the backend, simply using an IP and port. So this is how the GKE registers the backend with the IP and port. Thirdly, we can register the object storage itself by simply extracting the storage. So there are 3 ways we can register the backend: the VM instance group, the IP port, and the storage. In the case of the IP port, there are also serverless services besides GKE, like Cloud Functions or Cloud Run. These types can also be registered to the backend based on IP and port, allowing us to attach a load balancer at the top. I think this is what you need to keep in mind. So, in terms of types of global load balancers, HTTP and S load balancers, SSL proxy load balancers, and TCP proxy load balancers. Then for regional load balancers, there are internal TCP and UDP load balancers, network TCP and UDP load balancers, and internal HTTPS load balancers. So moving on, we can attach VMs to the backend, and there are 2 types. First, there was a managed instance group, and then there was an unmanaged instance group. So when you're deploying a VM in the backend, you must definitely attach it to an instance group that ends with group by firing a new shell once. So first, let me talk about the easiest unmanaged instance group. This is just one VM. I'll refer to this VM as the UMIG, the UMIG. You simply attach one VM to the backend as UMIG, but it does not support features like auto-scaling. So if you ask why we use this, it's because there are no significant fluctuations in costs. Since there are such requests, I use UMIG or the characteristics of the application. There are cases where I cannot use auto-scaling due to licenses or contracts when certain scaling occurs. So when choosing, I use UMIG. Most services use something called managed instance groups. And depending on the traffic, if the traffic increases, you can create multiple servers using a template. And when you delete a server, we can create a template first. If you create it as a managed instance group, you can start with 2 servers based on the load. And if the load becomes too high, it can scale up to 3 servers, enabling auto-scaling. Yes, so we can perform auto-scaling based on CPU load. Or we can also do auto-scaling based on the number of new transactions. And new transactions coming in per second. Now, how should we choose a load balancer? What kind of load balancer should we use? This algorithm flowchart is very important. First, let's take a look at what happens when traffic comes in globally. When traffic comes from outside to GCP, and if that traffic is web traffic, HTTP or HTTPS traffic, then we should obviously choose the global HTTP load balancer. But if not, if my service is not based on HTTP, but it's just a general TCP based L4 service, then when comparing TCP, if SSL if offloading is needed, we should choose the global load balancer with SSL proxy load balancing. But if SSL offloading is not needed, then it divides again. Should this be load balanced globally? For one global LB, there is one in Seoul, and there is one in the Tokyo region, or one in the Taiwan region. Should the service be like this? If it should be, then you can use TCP proxy. But if not, when I said that I don't provide service for dinner, the client IP needs to be preserved. So you can choose the network load balancing of the regional load balancer. When it was said that the client IP does not need to be preserved, you can use the global LB without TCP protocol. In this way, you can draw a diagram based on your needs and assess the situation to use the appropriate load balancer. Now, let's look at the internal aspect. When I said that my traffic only communicates internally between GCP instances, it means that even when connected to on-premises, such as through an interconnector or VPN to Google Cloud, we consider it as being used internally within GCP. So when there is traffic only within the CCP, it can be distinguished based on whether the traffic is TCP, UDP, or HTTP. So for UDP and TCP, you can use the internal TCP UDP load balancer, and if not, when I said I provide HTTP services, it means using the internal HTTP. You can use a load balancer. So actually, the ones that are used the most are these because in enterprises, while we do sometimes provide services externally, we usually build internally. So internal HTTPS and internal TCP UDP load balancers are often used. Next, this is also used a lot because in the case of services provided to external customers of the company, we use external load balancers. So we end up using internal HTTPS load balancing. Yes, so we've looked into this about load balancers, and in our next session we'll probably look into interconnectors and VPNs. Thank you for your hard work. Hello and welcome to the course on obtaining the Google Cloud Professional Cloud Architect certification. In this session, we'll explore how to communicate between existing on-premises legacy systems and the cloud when communication is necessary. So, when do we need to do this? We'll likely have a data room in our existing company, there'll be a data center, and there will be servers present there. In some cases, all servers in the data center may have been migrated to the cloud, or perhaps only about 50% have been transferred to the cloud. Or we might still be using the systems in the data center while deploying new services in the cloud and needing to communicate it in this way. So in the first case, if all systems in the data center have moved to the cloud, there is no need for communication with the data center. So there is no need to open a separate network. The VPN or Interconnect we'll discuss today is used in the following two cases. In this case, Since services are still being provided in some form by on-premises systems, communication between the cloud and on-premises must occur, and we will learn how this communication is done in this session. First, let's briefly look at the overview. Currently, there are two methods for on-premises and cloud to communicate. The first is a connection called VPN. The second is a service called Interconnect. If we compare the differences between these two, VPN refers to the bandwidth of the network, which is called BW. When the bandwidth is small, it ranges from 1 gigabyte to about 3 gigabytes at most. When we need such a small bandwidth, we use a VPN, right? No, I need a larger bandwidth. That's because there is a loss of network communication happening between the on-premises systems and the cloud. So when the network bandwidth is very large, we use Interconnect when communication needs range from as little as 10 gigabytes to as much as 100 gigabytes. Another difference is that while VPNs do encrypt communications by default, they have to go through the internet. Interconnect, on the other hand, Interconnect connects to Google Cloud through cables or similar methods. So, no internet connection is needed. Of course, while VPNs also communicate through encrypted tunneling over the internet, since the packets are routed to the internet, there may be cases where you cannot use a VPN due to company policies. In that case, you can use interconnects. For VPNs, there are two types. One is a single VPN with a regular tunnel, and the other is a HAVPN, which is designed for redundancy. HAVPN has two tunnels connected, and initially, communication occurs through the first tunnel. If that tunnel fails, it automatically switches to the second tunnel. Similarly, interconnects also have two options. The first option is called dedicated interconnect, and the second option is partner interconnect. Partner interconnect is used when connecting my on-premises system to the cloud. So if I want to connect directly from my system to Google Cloud, that is dedicated interconnect. In this case, the company needs a network administrator who will handle tasks like router configurations or BGP configurations directly. Partnered interconnect, on the other hand, involves a lot of network work which can be time-consuming, so a partner will set up the connection to Google Cloud in advance. When I configure partner interconnect, I'm connecting to the systems that are between me and the partner. This structure allows for a seamless connection while offloading some of the network setup responsibilities to the partner. Instead of connecting directly to a Google Cloud, I connect my network to a partner service, and then the partner service connects to a Google Cloud, which means that a partner company that supports this interconnection is involved in the middle. This is called partner interconnect. Now that we've looked at this process, let's go through each one directly. So, yes, the first one is VPN. To set up this VPN, two services are absolutely necessary. The first is a VPN gateway, and the second is a cloud router. These two are required. The VPN gateway needs to go from my Google Cloud service to the on-premises service. So the cloud router recognizes this IP as on-premises, and then it will issue a routing command saying that I need to go through the VPN gateway. When it receives that command, the packet will go through the VPN gateway and then moved on to the internet. If you look at the diagram here, there are currently two tunnels. So this is HAVPN. When it goes out from the Google Cloud service through the VPN gateway, it will go through the internet. This will communicate through an encrypted tunnel called IPsec, traveling over the internet to find the appropriate on-premises system, and hitting the on-premises VPN gateway, and then moving to the on-premises server, so each gateway will have an IP for BGP, which allows for network communication. In the case of HAVPN, SLA provides 99.9%, and the VPN can be used with a minimum of 1 gigabytes per second, with a maximum of 3 gigabytes per second. We have looked into VPNs, and now let's take a look at interconnects. As I mentioned earlier, there are dedicated interconnects and partner interconnects, and the difference lies in the maximum bandwidth. Dedicated means that the on-premises system is directly connected to Google, and for bandwidth, when you need lines ranging from 10 gigabytes per second to 100 gigabytes per second, you use dedicated interconnect. Partner interconnect, on the other hand, is provided through service providers that support this interconnect service, which have many connection points. If my data center is far from the network point in Google Cloud, it could really turn into a major construction project. However, when using the internet with a partner, we physically create many network points connected to Google Cloud in advance. In that case, the probability of my data center's network point being connected to the partner's internet network point over a short distance is very high. So we use the partner's internet. Next, in the case of partner interconnectors, the bandwidth is slightly smaller than that of dedicated interconnectors, but it still offers a very wide range of bandwidth from 50 megabytes per second to 50 gigabytes per second. So just know that there are partner interconnectors and dedicated interconnectors. And let's take a look at what a dedicated interconnector looks like. First, there are Google Cloud resources, and Google Cloud can never know the external IP that is connected to the outside. So there needs to be a cloud router. So there will be a network edge in Google Cloud. This means that there will be a direct connection from the on-premises router to the network edge. Then the user will connect through the on-premises router and then to Google's network edge, which connects to Google Cloud services via the cloud router. So connecting this on-premises router to Google's peering edge is not an easy task. So this is what the dedicated interconnect looks like, and if you look at the partner interconnect, you can see that this has been added. The service provider network and the partner's network are placed in the middle. The partner company connects their edge to Google's peering edge in advance. Then, they create multiple edges where they can provide their services and connect on-premises router to the service provider edge, followed by internal connections for communication. Just understand that the service provider is in the middle. So, there are companies that have the condition that network packets must never go to a third-party network due to security requirements. In cases like public institutions or financial institutions, you have no choice but to use dedicated connections. On the other hand, if the security requirements are somewhat lower and you want to take advantage of cost savings, or if your company lacks network personnel to manage dedicated internet connections, you can use partner interconnects. So today, we learned about VPNs and interconnects, and the specific issues and details regarding this will be covered in the Google Cloud Certification exam for the Network Professional certification. However, in our Cloud Architect certification, there are often questions asking whether to use VPN or interconnect, requiring you to choose one of the two. Just keep this in mind, and we will review the questions during the problem-solving session after the theory lecture on the network part. Thank you for attending the lecture. Hello, and welcome to all of you who have come to the lecture on obtaining the Google Cloud Professional Cloud Architect certification. In this session, we'll take a look at various network services offered by Google Cloud. We'll explore services that we've been using not only in the cloud, but also on-premises, such as DNS, routers, NAT, and CDN. One characteristic to note is that when these services, which were previously provided in traditional networks, are offered in Google Cloud, The name of the service is prefixed with cloud. So we have names like Cloud DNS, Cloud NAT, Cloud CDN, so it'd be good to keep that in mind. Now, let's get started by looking at DNS first. I'm sure you all have a basic understanding of DNS. When I throw in a URL like www.google.com in text form, the service that provides the corresponding IP is the DNS service. So let's take a look at what makes Google Cloud's DNS different. First of all, Cloud DNS is Google's DNS service that converts domain names into IP addresses, which is the basic function. And the features and advantages will be discussed below. It has a short latency. The reason it has a short latency is that Cloud DNS uses the same infrastructure as the DNS service. And the service provided by Google, a global company. Therefore, in the case of on-premises solutions, I'd typically create a server like a VM and install a bind or a commercial DNS solution on that server. And there would be a person in charge of managing this DNS. This person would have to manage both the server and the solution. And if we use Cloud DNS, we simply subscribe to the DNS that runs on Google's infrastructure. And then Google takes care of the management of the server and the solution. Because it's a service that runs directly on Google's infrastructure, it has a very short latency, and uniquely, the SLA is 100%. This means that 100% availability and also scaling are provided. Therefore, it can be very convenient for users, and since it has a very powerful infrastructure, DNS record creation and updates are very fast, and large-scale updates are also possible. Additionally, when using Cloud DNS, it usually provides a web console and web UI for DNS installation. You can manage this through the UI in the Cloud console, and you can also use Cloud DNS in various API forms. One important point when we talk about DNS is forwarding. What this means is that when I ask a question to the DNS, it doesn't have that information. So, forwarding is the role of passing that query to another DNS. Google Cloud's Cloud DNS supports both inbound and outbound forwarding. So, let's take a look at inbound. So the servers on premises can query the Cloud DNS through this Interconnect or VPN. This is what we call inbound DNS forwarding, and there is also outbound. Outbound refers to when services in Google Cloud query the Cloud DNS, but the Cloud DNS doesn't have that information. In that case, the query can be sent again through the Interconnect, or similar to the DNS on the on-premises system. For outbound and inbound forwarding, you need to set it up within the Cloud DNS. Once you set it up, it's good to know that it can be routed back as inbound and outbound. We have looked into DNS, and next we will take a look at routing. You all might be familiar with routing. Routing is what directs the traffic along the appropriate path, based on the source IP and destination IP. When a package comes in, I see that the destination is supposed to go to VM2. So I need to route it here, and then I see that it needs to go out through the internet gateway, so I route it through the internet. This is the role of the router. So when you use a cloud router, various routing paths are created depending on the destination. Routing paths are created for each region, and names are assigned to each routing path. There is also priority. So when the priorities are the same, or rather when the destinations are the same, you can set which policy should be applied first. Routers often do not need to be configured directly, but especially when using interconnectors or VPNs, Configuring the cloud router becomes quite important. The cloud router is a part that must be configured when using a VPN or interconnector, and if you let them know when using Interconnect or VPN, there will be routers on-premise as well. And they will exchange routing information through BGP sessions, then the routing table will be updated, and there is a separate IP for this BGP. So, if you input that IP, they will establish a BGP session and exchange information like send this IP here. Once the information is exchanged, the communication is possible from the VM in Google Cloud to the VM on premises and vice versa. From the VM on premises to Google Cloud. That is the function of the cloud router. Next, let's take a look at NAT. You might already know that NAT, Network Address Translation, is a technology that converts network addresses. So, what function does it serve? It's used when you want to communicate over the internet or externally without a public IP. Therefore, it's a serverless service, or rather, a software-defined network. So, through some solutions, we provide network address translation functionality. And now, what's good about it is that, first of all, it has good security. By using NAT, VMs do not need to have individual public IPs. This is because all outbound internet communications go through NAT. So there is no need to assign a public IP to each VM, which is advantageous for security. Additionally, using Cloud NAT provides a fully managed service which offers availability and scalability. Moreover, unauthorized users from the outside cannot access the internal VMs or IPs because they are blocked by NAT. Since it cannot be accessed, I think you can understand that it's now very secure. So now, regarding policies for outbound and inbound traffic, you can set them within the NAT function service, allowing you to configure traffic according to your intended purpose and use. As you can see, there is one NAT on the east side, and it is connected to subnet 1. In this case, the VMs in subnet 1 can communicate with the internet. But those in subnet 2 will not be able to communicate with the internet. So, all these functions can be set as policies within this cloud NAT. And when using GKE Kubernetes engine, if you set NAT for each pad, internet communication can be enabled for each pad with NAT. So whether it's a VM or a Google Kubernetes engine, the point is that NAT functionality can be provided without discrimination. If you want to use this NAT, instead of using Cloud NAT, you can simply create a VM and use it as a NAT VM. In this case, filtering or for inbound and outbound packets can be a bit difficult, and logs won't be generated. Additionally, there's the issue of needing to manage the server. So, using Cloud NAT would be more convenient for management than setting up NAT on a VM. Next is CDN. CDN stands for Content Delivery Network, and it is a network used to quickly deliver static content like images, HTML, and videos without delay. Let's take a look. I thought there was no blue CDN edge right now, and the server is currently in Europe. The server is in Europe, and when someone in Africa, Europe, or Asia accesses this service, the latency will be significantly different. When accessing a server in Europe from Europe and accessing a server in Europe from Asia, the size of videos will be larger, and there will be tremendous latency to provide that. So what reduces that is the CDN. When you set up a CDN, any image on the host server is automatically distributed to this edge. If a request is made in Asia when the distribution happens, then instead of being provided by the host server in Europe, it will query the already distributed CDN edge, and this CDN edge will provide the content. This way, it will have a very short latency. So you can understand that this is how a CDN operates. But if I made a request and there was content available at the CDN edge, we call this a cache hit. But if the requested data is not available, we call it a cache miss. However, after creating this CDN, it takes a little time to distribute it to each cloud CDN edge. Since the distribution time takes a bit, just because you create a CDN doesn't mean that it can be used immediately. It takes some hours for the content to be distributed. So please remember that now you can set something called the TTL for each CDN. So when I receive content from the host server, I can set the configuration value for how long. I can maintain it for a few hours. If the content is frequently updated on the host server, then if I set the TTL a bit shorter, the content will disappear from the CDN after the TTL time has passed. This is the type of solution that is used. So usually when using a CDN, a load balancer is attached at the back, and behind this load balancer you can use a VM or a bucket as the backend. So this is how we use a CDN. And what do we need to use a CDN? We need a load balancer and then a VM or bucket to use as the backend, so you can keep them in mind. Yes, so we've looked into DNS, routers, NAT, and CDN. Up to this point, we have explored Google Cloud's network services, and in our next session, we plan to solve a lot of problems. Thank you for your hard work and attending this long lecture.